So we will have, so I aim to provide a systematic introduction um, to database theory. So it's going to take a lot of seminars. Okay. The bad news is there will be a lot of seminars, and it would take some courage to sit through all those seminars. Okay, so this is the bad news. The good news is, well, if you indeed manage to sit through everything, and then you'll be able to do research. You'll be able to start doing research in this area. Okay. So today I'm going to start with something basic. What I'm going to do today is I will define what it means by database joins. Okay, so I can see some of you took my PhD course, and in that case, you already know a good part of it. Okay. However, we will also talk about what it means by cyclic hypergraphs. Cyclic. Now, this is something that we did not manage to talk about in the PhD course, so this is going to be something new. So as you will realize, there are two types of joins. Usually, we refer to them as cyclic joins. Cyclic joins and cyclic joins. Okay. Even if you have taken my PhD course, this would probably be the first time you hear about cyclic joins. Okay. Now, that will be the second part of today's talk. And then in the third part of today's talk, I'm going to prove to you that the join problem is computationally hard. Okay. Now, this is again something outside the PhD course. So I'm going to show you an NP-Hardness proof. Okay, so basically, you should not hope to really solve the join problem in its most generic form. And you will see what I mean. And this will allow you to connect to what you have learned in the PhD course. So if you still remember in the PhD course, I always said something like, you will have to assume that the join has a constant schema. All right, so all these things will start to make even more sense after today. Okay. All right, now let's talk about this DB join. Let's start from here. Database join is an extremely important concept for a lot of reasons. The first reason is that this is a very powerful formulation that captures many classical computer science problems as special cases. Okay, so this is one. And second, this database join is standing at the core of database theory. Okay, so we will first define it. Okay. This database join is actually a concept that is taught at the undergraduate level. Okay. However, as far as I can see, typically this concept is taught in a wrong way. I can say, okay. For example, one thing that I observed is that almost no undergraduate students will be able to define formally what a database join is. Okay, so we'll get to that in a little bit. However, I would say an even more serious issue with undergraduate teaching in a lot of universities is the following. So not undergraduate students understand the significance of database theory. Okay, I think today here, this is a wonderful opportunity for me to fill in the gap as much as I can. Okay, So I have to first tell you that the inventor of this database theory, this relational model, right? What's his name? I forgot his first name. His last name is Codd. You can look it up on the internet. Anyway, so Codd received the Turing Award for this invention. I can tell you. Okay. So this means this has to be a huge area that is incredibly useful. Okay. Why is it so useful? Okay, so let me put things in the following way. So if you look around you, right, you cannot deny you are surrounded by data. Okay, we have a lot of data. I am using the word data in a very loose way, right? We're surrounded by data. I mean, there are all kinds of data. So I can tell you there are two questions that human beings really strive to answer. The first question is, how would you be able to organize the data? Okay, when I say organize, okay, you really have to be able to create a mathematical structure over the data. Okay, so this is the first question that human beings strive to answer. Okay, now another question that human beings strive to answer is how can we extract information from the data? All right, so there are these two questions. Well, if you think about it, these two questions are still there even today. Even today, okay, you ask yourself, I mean, how would you organize data, right? And this question is still there. Well, Codd provided one answer to it. Codd said, okay, I'm going to use relations. Now, this is something we're going to define very shortly. He said, okay, you know what? Let's use relations. Let's use something like the Excel table. Okay, so that's how he proposed to organize the data. Okay, so data is stored in tables, right? But more importantly, he also provided an answer to the second question. So the second question is, once again, how do you extract information from the data, right, in its organized form? And Codd's answer to that is relational algebra. Okay, so if you think about it, right, algebra in general is basically a set of rules about certain operators, right? And if you still remember relational algebra, you know, in this relational algebra, there were multiple operators like projection, selection, et cetera, and John is one of them, okay? But what is really powerful about this relational algebra is that you can concatenate a lot of operators together into a long expression, okay? And these expressions, you can explain in English words, you know, what is the information that is extracted by each of those expressions. You see what I'm saying? So if you flip the coin, if you look at the other side of the story, essentially now this creates the opportunity that I describe to you something in English. And then you can write me a relational algebra expression. This is what we call a query, right? Query, database query. So that, you know, a system which stores all these relations, right, in this organized form proposed by Codd, and then the system will be able to extract information automatically for you. You see what I'm saying? Okay. So here, as we can see, Codd provided answers for the two questions. However, let me remind you that those were only his answers, right? His answers are good answers. Right, so he was the first one to provide answers of this sort, right? So that's why he received the Turing Award. However, today, these two questions are still there, okay? And I mean, we need modern answers to those questions, right? So beyond the relational model, there have been a lot of other models as well. And if you think about it, the essence of all those models is to provide answers to the two questions that I posed earlier. Okay, and even today, these two questions are still with us. Okay, as we evolve, I mean the civilization evolves, right? These two questions will have new meanings, and therefore and therefore they demand new answers as well, right? So this is what the database theory is about, right? So how would you be able to organize data in a way that allows people to extract information in an effective manner, all right? So once you have figured out the effectiveness, which means you are able to have a language that's incredibly expressive, right? So as expressive as relational algebra, for example, and then you get to talk about efficiency, right? How fast would it be possible to answer every single query? So I would like to start this seminar series with this monologue, which again sheds some light, I hope, right? Sheds some light on the significance of database theory. Okay. So let's talk about this database, John, right? So I'm sure the following concepts will ring a bell for many of you, right? So let's say I have a table, this table has two columns, A and B, and inside the table, think about them as an Excel table, right? You could have something like 1, 2, 1, 3 as the records, as the rows, right? Say here I have another table. Say this table is B and C. Let's just say we have some other tuples there, right? And then from your database systems course at the undergraduate level, I'm sure your professor has told you, hey, John will give you a natural John in particular, okay? Will give you a table, and this table has 3 columns, okay? 3 attributes, A, B, C. And what do you have in this column? Well, you try to look at every pair of tuples in the 2 original tables, and you try to see if they will give you an answer, right? So for example, if these are the 2 tuples we're talking about, they do not give you an answer because they use different values on B, okay? They use different values on this common attribute, okay? So if you look at this combination, and then yes, they, as you can see, they are consistent, right? In the sense that the B values of those 2 tuples are the same. So in this case, you create a tuple like this. Basically, you put all the values together, right? But the value on B would have to be the same, right? So if you, with some effort, you're able to see that this is the only tuple that can be produced by the join. Okay, so this is what was taught at the undergraduate level. Okay. Well, as theoreticians, well, you are theoreticians now, I believe. Okay. So as theoreticians, we're not happy with this formulation, right? Because we want to be able to define everything using very solid mechanisms, right? So, for example, I use the word table. Oh, come on, what is a table in mathematics? Right? There's no such a thing as tables, right? So in mathematics, we have sets, we have integers, etc., etc. But we don't have tables. You see what I'm saying? So before we can even commence to think about database theory, we have to, when we think about database joins, we have to be able to formalize everything first. Okay, so this is the the thing that I'm going to start with. Okay. All right, so I'm going to walk you through the definitions. So for those of you that were in my PhD class, you already know the definitions. Okay, so bear with me. Wait until the AC list of it. Okay, a cyclic hypergraph. So we'll get there. Okay. So let me formalize everything for you. Okay, all these things, all these undergraduate level discussions can be made very rigorous in math. Okay, so first of all, I'm going to start with a set. Okay, so this is the name of the set. Okay, I call it ATT. All right, so this is an infinite countable set. All right. By the way, you see every word that I say should be understandable as long as you have a bachelor's degree. Okay. If something is outside the scope of the undergraduate level, and then I'm going to define it. Okay. So infinite countable set, this should be understood to everybody, right? So it should be understandable to everybody, right? Okay. So this can be any set. All right. I don't really care what the set is. So if you want, you can use, for example, the integer domain. That's perfectly fine. Okay. However, the elements of this ATT set will be referred to as attributes. Okay, so this is a set of attributes. And so a set of attributes. Okay, so this is the first time the word attribute comes into the picture. Okay, so basically attribute is defined as an element of this set. Okay, so every element of this ATT set is referred to as an attribute. Okay, it's quite common and natural to use English letters to refer to the attributes. For example, in this example that I gave earlier, you could have big letter A, B, C as elements in this ATT. Okay, but mathematically speaking, now you know that we have a set, and this set, the name is ATT, and if you take elements from the set, then you have attributes. Okay, good. All right, so the next thing that we're going to define is tuple, right? So as you can see in the table, you have rows. So each row there is referred to as a tuple, okay? But again, we don't have the notion row in mathematics, right? So this is something you might want to pay attention to, right? Because in your research, right? So many students feel, hey, oftentimes it's very difficult to articulate your ideas formally, right? But why, right? So let's see, right? So at this point, this tuple might give you some of that familiar meaning, but let's see how it can be formalized in mathematics, okay? So here, we will first get a subset of this ATT. You see, this is well-defined, right? ATT is a set, and this X is a subset of that, right? So basically, this X, right? This beautiful X here, curly X, right? Beautiful X here is a set of attributes, right? So a specific set of attributes. All right, so this X is a finite set, okay? A finite in size, okay? So we don't talk about infinite set of attributes here, all right? So this is a finite set. And then a tuple, now pay attention here. A tuple formula is defined as a function. As a function from this attribute set X to the integer domain. Okay, so it's defined as a function. Okay, so for each attribute, say A, inside this beautiful X, let's emphasize on this definition here. So for every attribute A, okay, in this beautiful X, right? So you can write something like this, okay? U parenthesis A to refer to the value of this function on this attribute A. You can see all these terms are supposed to be perfectly clear now, right? So this is what I said. This is the value of this function, which is a tuple, right? Function on this attribute A, all right? So this is fair because A is from this beautiful X, right? And X is a subset of ATT, right? So everything falls into the right place, okay? So this is referred to as the value of the tuple, okay? So value of U on A, okay? So this is how a tuple is defined, right? Later, I will need projection. Projection. Okay, so here I'm going to define what it means by projection. All right, so you have a tuple here, U. So whenever I talk about U, implicitly have assumed the existence of a beautiful X, right? Because otherwise, how would you define the function in the first place, right? So you take that X and you take a subset Y of X, okay, subset Y of X. This is beautiful Y, right? So it's a subset, right? And then I can define a tuple V over Y. Okay, by the way, over, I use the word over. I think this deserves some clarification, okay? It may not be completely standard, right? When I say this tuple, this function is defined over X. So this means, this is the input domain for this function. You see what I mean? So for example, U is said to be a function over X, right? So that should be clear, right? So here I say V, so that's a function. All right, so V is over Y. All right, so if you have a subset Y, and then I can define a tuple V in the following way. Okay, so I'm going to clarify the definition, but before that, let's be clear that this V is a function over Y. All right, so it's a tuple over Y. So this V, okay, so the projection. Okay, so now look at this U, right? U is inherited from above, right? So this is a tuple, right? So I take a subset of attributes, beautiful Y, and pay attention to the shape of the brackets, right? So this is a pair of square brackets, right? So it's not parentheses, right? So you have to, you see everything is rigorously defined, right? So here parentheses, inside of parentheses, you're supposed to put just a single attribute, right? So because you're talking about function value, but here you're talking about projection, right? So this is a set there, right? A set of attributes. So this is a tuple. Okay, it's a tuple V over Y. All right, such that for each A, which is an attribute in this Y, it holds that VA is equivalent to UA. Okay, so this is the formal definition of this projection. Okay, so we say that this projection is the projection of this tuple U over this Y. Okay, good, nice. All right, so now you have attributes, you have tuples. Next, let's define relations. By the way, relation. Why do we call our database systems relational databases? So I can tell you this is actually a difficult question for a lot of people, right? So I would say a lot of professors actually teach this wrong, right? So oftentimes I hear, well, it's called relational databases because you have tables, and among tables you have relations, right? So that's why it's called relational database, right? Wrong, okay? Well, relation is actually a term, a concept from discrete mathematics. Okay, so what is a relation? What is a relation? You know Cartesian product, right? I give you two sets, right? S1, S2, you can do Cartesian product, right? Cartesian product basically takes all pairs of elements from these two sets, right? I give you three sets, you can do Cartesian product, right? S1, S2, S3, right? So you see Cartesian product is a well-defined concept. So here comes relation. Relation is just a subset of a Cartesian product. All right, so that's from discrete mathematics. So once again, what is a relation? A relation is a subset of a Cartesian product, right? So if you look at every table, in my earlier example, right? So every table is essentially a relation. It's actually a subset of the Cartesian product. For example, this one, the first one, right? A subset of the Cartesian product of the domain of A and also domain of B. All right, so that's why our database systems are called relational databases. Okay, not because there were entity diagrams among different tables, right? So that's a wrong way to look at it. Okay, so now you know. So for the very first time, we're going to define what it means by a relation for our discussion. Okay, so a relation okay, is, let's say call it R, okay, is a set of tuples over the same set of attributes. Okay, so this relation R, once again, is a set of tuples. However, these tuples, they cannot be over different attribute sets. You see what I'm saying? All these tuples, we have to be over, we have to be functions with the same input domain, right? But you already know that the input domain of a tuple is just a set of attributes. Okay, so therefore, I have the right to say, hey, there is a beautiful X here, right? So this X is very important. Now, this X is actually called the schema of this relation. Okay, so now everything feels clearer and clearer, right? So if you look at the first table, you can see essentially you want to look at this A and B as this beautiful X here. Okay, so this is actually a relation with schema A and B. Okay, now this relation has two tuples, right? So these two tuples, each one of them is a function, right? So the relative ordering of the attributes is not important. Okay, all right. There's another very important thing here. Look, this is a set. A set. All right. So in mathematics, every time we talk about sets, we imply that the elements inside this thing, this collection, they are distinct. Otherwise, we call them multi-sets. You see what I'm saying? All right. Now, this is very, very important. Okay. So in a relation, you're not supposed to have two tuples that are the same as each other. Okay. So this is under the set semantics. Okay. So this is going to be super important several weeks down the road when we talk about the AGM bound. Some of you already know about that. Okay. Good. So so far so good, right? Okay, very nice. So finally, now I can define what it means by a join. Okay, a join. Well, this is the place where different textbooks will give you different definitions. For our discussion here, we will go for basically the simplest definition I'm aware of. Okay, so today, actually not today, in this seminar series. Okay, so I'll define a join, which I refer to as a using this Q. By the way, in database theory, a join is a special case of so-called conjunctive queries. Okay, it's actually a query. I told you, right? I mean, those two questions that we try to answer, right, in database theory, right? So you already have the organization about data, right? So these relations, you can imagine you have lots of relations. So that's basically Katz's answer to how we should organize data. So that's how you should organize data, right? And then the next question is, how would you be able to extract information from the data, right? So that's actually a query. You see what I'm saying? So that's the relationship. So that's why Q. A join is, as I said, a special case of this conjunctive queries, right? So I don't know if this seminar series would be able to survive until that point. If I can see there's enough interest, I will get into conjunctive queries as well. Okay, but today we're going to talk about this join. So this join is formally defined as a set of relations. Okay, and that's it. Okay, so for example, in my initial example here, the join is defined by two relations. Okay, so AB and BC. That's it. Okay. All right. By the way, when I say AB and ABC, I do not just talk about the schemas, right? Because a relation is a set of tuples. So whenever you give me a join, the relations are already fixed. Okay. All right. Now I have to define the output of a join, right? So this join Q. So this is the result. Okay, result of the join. Okay, so this is a relation. This is actually a relation. All right, so the output of the join is a relation. Okay, just like what you saw before, this ABC there, right? Okay, but whenever I talk about relation, I have to talk about the schema. Otherwise, things are not clear, right? So what would be the schema of this relation? Well, let's look at, let's define this V. So this V is, watch careful, right? I take every relation in the joint, okay? And I take the schema of this relation, all right? And then I take the union, right? So basically in English, it basically says you take all the attributes that appear in the interrelations of the joint, right? So this is V, okay? So for example, in here, we have AB and BC there, okay? So this is ABC, in other words, right? So this V. Okay, so this relation is over V. Okay, defined as follows. Okay, so this is a set of tuples, U over V, such that for all relations, for every relation in the joint, the following holds. Okay, so the U, let me first give you the mathematical definition, and then I'll explain it. Okay, so if this is the first time that you see the definition, you might get intimidated by it, okay? Because this looks unhuman. You see what I'm saying? This is for machines, right? However, once you get used to it, you will fall in love with it, okay? Because this is a very concise way to express what I said about this pairing and consistency and everything, okay? So essentially, I want you to think about the result as follows, right? So you know that the table has a schema ABC, right, for the output, right? And then you try to insert tuples into the table, okay? And if you manage to insert a tuple, so this tuple U here, right? You try to insert whatever tuples into that table. But the thing is, every tuple will have to survive a check, right? A scrutiny check here. If it's able to survive the check, and then it gets to be included, it gets to stay, right? It can stay, and then it will be a tuple in the joint result, right? So what is this condition? This condition says, well, you propose, let's say 1, 2, 4 there, right? And then I will have to look at the projection of this tuple onto every single relation. You see what I mean? I will check if the projection is in every relation. You see what I mean? For example, here, you propose 1, 2, 4, and then I look at A, B, I can see, okay, the projections A and B, and then I look at the projection of this tuple on A and B, so that's 1, 2. Do I have 1, 2 in the first table? And the answer is yes, right? And similarly, you have 2, 4. That's the projection on BC, right? And 2, 4 is indeed a tuple in the other table, right? So therefore, this is a result tuple, okay? However, if you try to mess with me, you say, hey, 1, 3, 4 is also a result in the joint, and then I can prove you wrong, right? Because again, we will check 2 projections, right? So first of all, check the projection of AB, check the projection on AB. So I get 1, 3, and you're fine because I see 1, 3 here. But on the other hand, if I check the other projection, which is on BC, and then I expect to see 3, 4 in the second table, but I don't. You see what I mean? And therefore, I'm going to reject this tuple. Okay, so you won't be able to survive this scrutiny unless you really give me something that can be produced using this undergraduate interpretation. You see what I'm saying? Like you look at all the ways, all possible ways to take tuples from the 2 tables, and then you check for consistency. It's the same thing, except that this is so much more concise. All right, so this is the joint result.
Sorry, I simply comprehend this as like each tuple is a role.
Each tuple where?
Each tuple is a role.
I think what you meant to say is that if you take the projection of the tuple in the join result, and then the projection will be a row in some table. Is that what you're trying to say? Okay, I guess not. Okay, so if you can clarify your question, and then I'll be able to answer it. Okay.
I'm quite confused about this function of sets.
Say that again. You're confused about the definition of the join result?
Actually, over this concept, because like it's totally in a different way from what I learned in my undergrad.
Yes, that's what I figured, and I get that a lot. Trust me. Yeah, okay. So think about what you are familiar with. It's totally fine, okay? And then eventually you will see that they are talking about the same thing, except that this mechanism here is formal, right? Yeah, let's take a moment to accept this new mechanism, this new machinery, this is notational machinery. This is very important because otherwise it makes no point continuing, right? Right. So, for example, if you say, so I guess it will be very natural to look at all the possible ticks. You see what I mean? All the possible ways to combine tuples, right? So this is quite natural, right? And you look at two tuples, one from each table, and then you accept it. You accept the pair if they are consistent, right, on the common attribute. That's fine, right? Okay. So this is sort of like doing things from the perspective of the input relations. Now I want you to change the perspective. I want you to try to construct results from the perspective of the output schema. Okay, output schema. All right. So you see, before we were looking at the input relations, right? So now I want you to look at the output schema. I said schema, only ABC. Okay. So here's another way for you to derive exactly the same result. Okay. So as I said, you try to put whatever tuples you can conceive into the output relation. Okay. However, you ask me, who is the professor here, to give you a full mark or 0 mark. Okay, there's no partially correct. So if you propose a tuple, if I accept it, and then this will stay in the join result, and then you will check, hey, in the end you get, I mean, the only way you can propose tuples that can stay will be exactly the same tuples that you would be able to obtain using the O approach. Okay. All right, good. So what is the criterion that I will apply to either accept or reject your proposed tuple, right? So for example, you propose 1, 2, 4, I'll accept it. Okay, and what is the criterion? Simple, right? So I look at every table, for example, AB, right? AB. Okay, I think this might be related to what you asked. I look at AB, and then I look at your proposed tuple, right? So I look at the projection of your proposed tuple on AB, which is 1 and 2, right? And then I check whether 1, 2, this tuple exists in the first table. Okay, so good. So it's good, right? So good so far. Now I'm going to do the same thing with respect to the other table. And then again, I see 2, 4 is there, right? So basically this is created by these two ticked tuples, right? Okay, so you can prove, well, in the O approach, if if you are able to have 2 ticks and they are consistent, and then you will be able to construct the same tuple in this proposing approach, right? On the other hand, if you give me another tuple, now this is something that I used before, right? So let's say this time you propose 1, 3, 4. I'm going to reject it. Why? Because if you look at the projection over BC, you have 3, 4 here, right? But 3, 4 is not a tuple. in the second relation, and therefore I won't allow it to exist. Is what I'm saying. So you can try. Well, try as you may. You won't be able to give me another tuple that I can accept.
Yeah,
you got the ideas now, right?
So it's like it's not one input aspect like defining set of union. It's like we define all the possible output and for each output remains.
There you go, right? So now we are on the same page, right? Basically, you have said exactly the words that I said, except that you said them voluntarily. So I'm very happy about that. So that's exactly the idea. Okay.
Yeah. So I was wondering, like, whether there is like something simpler to define this, like another aspect.
Well, I think it's kind of subjective, right? So, for example, if you say, well, you can still, I mean, after the relations have been properly defined, right? You can still use a procedural definition. Okay, so I would say, okay, I give you a procedural, and then I take the output of this procedure, not procedural as a procedural definition, but you give me a procedure. And then you can say, I would take the output of this procedure as the result of the join. And then inside the procedure, you can say, okay, you know what, you do the tick approach, right? And then if they share common values, and then you take just the ABC and then you put it into, you could still do that, right? But as I said, once you got used to it, you will feel in love with it because this is so much more concise. You see what I'm saying? Okay, good. Very nice. Okay. So now everybody understands what a John is. Okay, what a John is. So I can tell you the John problem is simple, right? The John problem is simply that I give you a John, as I define here, right? Q. And then I ask you to compute the John result, Q. Okay, so for those students in my PhD class, pay attention here. I make no assumptions about how many attributes you can have in this V, in this big V, all right? So you can have a non-constant number of attributes, right? We're really talking about things in general. Yes?
So what is the representation size of this joint?
What's the representation size? That's very good question. Okay, we got to be careful here. So in computer science, I mean, if you talk about Turing machine, okay, the size of an input is how many bits you will need in order to encode the input. Okay, all right, good. So that for the record, right? Now, so I will first tell you a fair way to define the input size of the joint. And then I'm going to make connections, okay, why this is fair, right? Because you will see this is not exactly how the input size is defined with respect to a Turing machine, okay? Look, the input size of a joint is defined as the total number of values you will need in order to represent all the tuples in the input relations.
Yeah. Number of
values, the integers. For example, here the answer will be 4. Sorry, the answer will be 8. Yeah, exactly. So you can say this is the number of tuples times the number of columns you have. So that will be the input size of one relation, right? So that's basically the number of values in the table, right? And then you add up the sizes of all the relations, right? Okay. But pay attention, right? So if you talk about Turing machine, these two are not exactly the same because a Turing machine says, okay, you have to look at the number of bits. But here we're looking at the number of integers, right? But if you think about it, the same thing also applies to almost every other problem, right? So for example, when you talk about sorting, you say the input size is n, right? So when you have n values to sort, right? But hey, has it ever occurred to you that this is not how a Turing machine would define input? You see what I'm saying? Okay. However, when you talk about Turing machine, they talk about polynomial versus non-polynomial. Okay, so it doesn't really matter if you say the input is n or the input is n log n. You see what I'm saying? All right, okay, good. So why am I mentioning this? Okay, well, this is because for joints, we will be talking about NP-Hardness. Actually, we will talk about it later. But NP-Hardness is defined with respect to a Turing machine. You see what I'm saying? You have to say, okay, this is polynomial or non-polynomial in what? You see what I mean? So in the end, it's always in the number of bits that you need in order to represent the input, okay? However, later on, I'm going to analyze things by treating the input size as the number of values as I defined, right? But the conclusion's the same, okay? So I'm taking my time. The seminar will be longer than an hour. Okay, I hope you don't mind. I think I have the video recorded today. So now the John problem is clear. Okay, the John problem. Now today, the first new thing beyond the PhD class is this so-called acyclic John. All right, so this is going to be an extremely important topic. Okay. So before I can talk about this acyclic John, I have to talk about what it means by the schema graph of a John. Okay, so let's say the John is Q. Let me first define the set of attributes again, the set of attributes in the output relation of this John. This is what I wrote before, right? So this should make sense to you, correct? Okay, good. Now I'm going to define a set of hyper edges, okay, hyper edges, right? So this set of hyper edges is this. So if you look at every relation in the John, okay, every relation in the John, right? I take the schema. All right, so this is a set of attributes, right? Remember, this is a set of attributes, okay? And why did I say this is a hyper edge? So usually when I'm talking about this, I will make an analogy to traditional graphs, right? So when you look at graphs, right? We talk about graphs, let's say social network. Typically, you assume that every edge contains only two vertices. That's what I mean, all right? But this is actually not necessary in general, if you think about it, right? So for example, you talk about a paper. And you look at the set of authors of that paper, right? You can think about it as an edge, right? Except that this edge is a hyper edge. You see what I mean? This is what we call a hyper edge. Okay, it can contain an arbitrary number of vertices. Okay, so that's called a hyper edge. So accordingly, and then we can define what it means by a hypergraph. A hypergraph is essentially defined by a pair. So this is a pair of vertices, there's a V here, and also a set of hyper edges, okay? So the graphs that we usually talk about at the undergraduate level in the computer science program, they are graphs in the sense that every edge has a size of 2. Okay, so that is a graph. But hypergraph really generalizes that. Today, we're not going to talk about the AGM bound of hypergraphs. Okay, in case you are wondering, especially those from my PhD class, I'm going to talk about what it means by asymmetry of this hypergraph. Okay, so now let's think about this graph here. Okay, so this graph, right, as I said, it's defined as a pair, right? So this V here, this is a set of vertices, a set of attributes, basically all the attributes that ever appear in the relations, the input relations of the John. And then if you look at this Y, right? So this beautiful Y here, it says, I'm going to take all the schemas, okay? Every schema forms a hyperedge, okay? So for example, if I say, okay, the first relation is AB, and the second relation is BC, all right? So, and then in this case, you are looking at essentially a conventional graph, right? So this is AB, this is BC, right? So this is the hypergraph that we're talking about, okay? So if your join has relations with these schemas, and then this graph is referred to as the schema graph of the join, okay? Schema graph of the join. But you already know that a relation does not need to have just two attributes, right? A relation can have an arbitrary number of attributes. For example, Let me give you another one here. Let's say A, B, C, B, C, D, and then C, E. Okay. Say I have a join with 3 relations, and their schemas are like this. Okay. So what would be the schema graph of the join? Okay, simple, right? So first you look at all the vertices, collect all of them. So these are the attributes in V, all right? And then from every schema, you create a hyperedge, right? So this is the first hyperedge. And then you have BCD. So this is BCD. And then finally, you have CE, okay? CE. So there you go. This is the schema graph of this join, okay? Schema graph, okay? Good. Now, I'm going to define what it means by an acyclic hypergraph. Okay, so for example, is this hypergraph acyclic? Okay, well, it's not so easy to see whether this is acyclic or not. And I can tell you this is acyclic. Okay, but why? Right? Why is it acyclic? Right? So if you think about it, if we talk about conventional graphs, right, with binary edges, right, and a cyclic graph there is defined with respect to cycles, right? So if a graph has no cycles, and then it's acyclic, okay? You could still go down the same direction with respect to hypergraphs. However, it's going to be quite tedious because I have to first define what it means by cycle in an acyclic graph, okay? And in general, people do very, very seldom would people use such a definition because it's very difficult to check whether a graph is acyclic, okay? So I'm going to present another definition, and this is the definition that's much more common, okay? So this definition is also the main definition we'll use for the seminar series, especially in the next seminar, where I will tell you how to detect whether a hypergraph is cyclic or not in polynomial time. Okay. By the way, this hypergraph can have an arbitrarily large size, right? Because you could have an arbitrarily large number of vertices. You could have an arbitrarily large number of hyperedges here. Okay, because we're not constraining that the schema graph needs to have a constant size. Okay. All right, so now let's define what it means by acyclic. Okay, so G, which is a hypergraph here, is acyclic if, okay, there exists a tree. Now this tree is a conventional concept, okay, a tree, right, a tree. This tree T satisfying the following 2 conditions, okay? So the first condition is, what I would like to call the 1-1 property, the 1-1 condition. The 1-1 condition says every node, there's a 1-1 correspondence. So each node of T corresponds to an edge, a hyperedge. Okay, so an edge in E, and vice versa. Okay, so for example, here ABC, BCD, CE, right? You could, for example, you could say ABC, so that's 1 node. In here, this BCD, here's another node. All right, but so far you don't really have 1-1 correspondence because you don't have a node for CE. You see what I mean? Okay, so you could, for example, you could say something like this. You could say something like, CE, and then you have BCD. Okay, so this will be fine. Okay, now you have a tree satisfying the 1-1 correspondence properly. Okay, 1-1 property. Okay. All right. However, there were two conditions in total. There's another condition coming up. Okay. So the condition says, okay, so this is called the connectedness. Okay, so for each attribute, A in this V is here, right? So this vertex set, right? So for every vertex here, right? The nodes. So when I say node, you should react to this by thinking a hyperedge. You know, it's 1-1 correspondence, right? 1-1 correspondence here between nodes and hyperedges, right? The nodes containing A. You see, this is well defined, right? Because every node is a hyperedge, and I can say whether or not this hyperedge contains an attribute, right? So the nodes containing A form or constitute or form a subtree of T. Now pay attention, T is not a rooted tree. Okay, it's not a rooted tree, right? So when I say it's a subtree, essentially I'm saying that the nodes, they constitute a connected component. So what I'm saying that you can reach from one node to another by traveling just over the nodes containing this A. Okay. So for example, this tree here does not satisfy the second property. Okay, it's the second condition. Okay. Well, however, if you choose this attribute, okay, so this attribute A, because I also have A there, so let's change this A to something else to make things clearer. Okay, so let's say X. So if you choose this X to be C, attribute C, you actually see that this property holds on C, right? Because if I say, what are the nodes? What are the hyperedges? What are the nodes of this tree containing C? You will say all of them, right? And as you can see, indeed, they are connected, right? Because you can travel among these nodes, freely in the tree, right? But the thing is, there is one attribute, and I believe there's only one attribute here violating this connectedness property, and the attribute is B. Okay, so for attribute B, you have here and here as these two nodes containing B, but as you can see, they do not induce a subtree of this T. So that means you have a forest here. Yes.
The subtree here defines a node and O is choosing this.
Yeah, that's a good. It's actually partially my fault here. So I should have said induce. Okay. So when I say when you have a set of nodes, right? You induce a subgraph as follows, right? You look at every edge in the original graph. You see, I'm talking about graph here because tree is a graph, right? Binary edges, right? And if both vertices of this edge belong to your set, and then this edge is taken, otherwise it's not taken, right? So by doing this, you define a subgraph. So in this subgraph, the set of vertices is just a set that you care about, and the edges are determined like what I said, right? So if these are the two nodes that you care about, and then you induce no edges, good. And then so this subgraph, as you can see, it contains only two isolated vertices but no edges, right? So therefore, this subgraph is not connected. Okay. So when I say these nodes, they induce a subtree. This means that this subgraph induced by these nodes will have to be connected, right? However, since you started from a tree, right? So this subgraph, if connected, will have to be a subtree of T.
So it's like there is level 1, level 2, level 3, level 4. for level 3. And
Right.
and the induced subgraph is only level 2 and level 3 connecting nodes.
Yeah.
Can I?
Yeah, so first of all, there are no levels because this is not a rooted tree. Okay, so you get to talk about levels and parents and children only if this is a rooted tree. This is just a tree. Okay.
Yeah, I will consider like these leaves. If it is
Okay.
also a tree, like 1, 2, 3.
Correct.
And if the induced subgraph is 2, 3, then you can see there are some other children nodes 1 and 4. So can I consider this?
Sorry, I just want to make sure I understand the question, right? So that you're talking about limbless here. So what are the nodes containing X here? The second and the middle two. Okay, so you want the middle two, okay? This is, so if let's check by definition, right? Let's go by definition. So if these are the two nodes, right? So what would be the subgraph induced by these two nodes? So the subgraph will contain also this edge, right? Okay, good. Now, is this subgraph connected?
Yeah.
It is connected. And therefore, this is a subtree of this linkage.
So I think like in our in our normal understanding, a subtree will be like a node and all its children nodes.
Yeah, that will be the definition for a rooted tree. Okay, so when you say a rooted tree, right? And if you have a node, and usually people would say the subtree rooted at this node. You see what I'm saying? That would be the perfectly correct way to refer to it, right? So people say the subtree rooted at this node, and then it becomes clear, right? And when people go fast, they're like, oh, the subtree of this node. However, the subtree itself, just like subgraph, right? Subtree itself refers to a subgraph. And it's just that the subgraph is connected and there are no cycles in it. Yeah, okay. You got a question?
Yeah, I think we need to define what do you mean by C over this D, because they are defined over like infinite component sets.
Can you say that again? This tree T?
Yeah.
This tree T.
Vertex here.
Right. Well, so there's a tree T here. The first bullet constrains what are the nodes of this tree. The nodes, each node is a hyperedge, right? Hyperedge of the graph. So for example, there, right? I don't define the edges. So you can form a tree over these nodes.
So this is arbitrary.
Arbitrary. So I'm here, there exists. So if you can find a tree satisfying both, and then all good. Okay.
So it just give you a bunch of isolated vertices. You can find a way to connect, find a way to make this a tree.
Yeah, sure. Yeah, exactly. Okay. So for example, now the goal is to form a tree over these three nodes here, right? So this is one way to create the edges, as you said, to form a tree, right? So this tree does not work, right? This tree does not support my earlier claim that this is an acyclic hypergraph, right? Okay, however, there is a tree that will support my claim. So you see, I actually started with that tree, but I changed it. Okay, I don't know if you noticed it. I wanted to have this discussion here. Okay, so look at this tree. Okay, let me see. Yeah, let's look at this tree. Hey, that's a tree, right? That is a tree, right? Because you can see no cycles there, right? But this time, this tree satisfies both problems, as you can see, right? Okay. And therefore, this graph is an acyclic hypergraph. Okay, acyclic.
You have a common the intersection of the attribute of this node is anything.
Well, that's a fair way to say it. Okay, so next week we will talk about how to detect whether a hypergraph is acyclic or not. Okay, so we will, I mean, this is polynomial time doable. Okay, although it's not completely clear at this point how to do it. Right. Okay, so let's look at another example, right? So let's say this time I have three hyper edges here, A, B, B, C, and AC. Okay, would you be able to find me a tree? Would you be able to find me a tree here? Okay, would you be able to find me a tree here? I don't think you can, all right, because this is a cyclic graph, okay, a cyclic graph. So now I think I will be able to shed some light on the difficulty of defining a cycle when it comes to a hypergraph. Look at that graph. You see what I mean? Some of you would say, hey, how about BC and CB? You see a cycle there. It could go from C to B in the green edge. And then you can come back from B to C in the red edge, right? You do have a cycle there, right? But hey, this is a cyclic hypergraph. You see what I'm saying? So that's why I said I do not want to go down that direction. Okay, so this is cycle definition. We got to be very careful with it. You know, sometimes it could be quite messy. Okay, and for sure I won't need it. I don't need it. Okay, so this is a definition that is much easier to check. Okay, good, very nice. So now we will probably finish in another 15 or 20 minutes, okay? So now here comes the last part of today's talk, okay? By the way, with this acyclic graph concept being clear, and then we can define formally what it means by an acyclic joint versus a cyclic joint, okay? So now you have a joint, you have a schema graph. If the schema graph is an acyclic graph, and then this is an acyclic joint, okay? If otherwise, this is a cyclic joint. See what I mean? Okay. Well, let me tell you why these two joints are so important. Okay. Well, I think 2 weeks later, we will see that every acyclic joint can be solved in polynomial time. Okay. In fact, we can even solve it, you know, with wonderful time complexity. And I can tell you that no one is able to do the same for cyclic joints. Actually, I do not even know one example of cyclic joint for which one is able to prove the same time complexity that can be achieved by this so-called Yanakaki's algorithm on a cyclic joint. So we'll talk about all these things bit by bit, okay? But the short message here is that if you indeed have asymmetricity here, and then the joint problem is significantly easy. Good. Very nice. So now let's talk about cyclic joints. Now remember, I said what a joint problem is, right? So the joint problem says, okay, I give you this Q, and I want you to compute joint Q, right? So that's simple and clear, right? Now I want to argue that, you know, it's very, very difficult, if not impossible, for you to come up with a polynomial time algorithm to find this joint result. Okay, but the thing is, I gotta be careful because it's not so clear what I mean by polynomial time, because the size of this joint result can be exponential in the number of in the input. You see what I mean? I define the input size as the total number of values that you need in those relations, right? In those tables, right? You can imagine, you know, sort of like Cartesian product, right? So the number of tuples in this joint size, joint result, right, could have an exponential size, right? The size could be exponential in the input size. So when this is exponential, and then even reporting the joint result itself will take you exponential time. So I mean, so sort of like you earn the right to use exponential. So it's not that clear this way, right? And therefore, I'm going to construct a different argument to illustrate the computational hardness of the problem. Okay, so this is called the emptiness detection. John emptiness, all right? So all I want you to do is to tell me whether this is 0 or not. Okay, just tell me, do you have at least one tuple in the join result? All right, so now I remove the opportunity for you to argue with me, hey, you are entitled to exponential time. You don't, okay? Now the result is just a Boolean answer, all right? Either yes or no. You see what I mean? Okay. And then I'm going to prove to you that this John emptiness problem is NP-hard. Okay, it's NP-hard. So for those of you that were in my PhD class, now you can connect the dots, right? So there, I always talked about joins whose schema graphs have a constant size. You see what I mean? Basically, this means the number of attributes in the schema graph is a constant, all right? So now you know why, okay? Because in general, even this problem cannot be solved in polynomial terms. So NP-hardness proof is typically done by reduction, okay, reduction. So we're going to convert a problem to the join problem, okay? So in the NP-hardness terminology, we don't say convert, right? We use a synonym. So we will reduce basically convert, okay? So we reduce 3-set to join emptiness. Okay, so basically I'm saying, suppose we have an algorithm that can do join emptiness, and then, sorry, this algorithm runs in polynomial time, right? So time polynomial in the input size, you see what I mean? And then I'm going to use the same algorithm to solve 3-set. But 3-set is well known to be NP-hard, right? Okay, so remember what is 3-set. Okay, 3-set basically says the following. Okay, you have some Boolean variables. Okay, so let's say you have n Boolean variables. Okay, and I give you an expression. Okay, I give you a logic formula. Okay, so this formula has this form. Okay, so let's say this formula is phi. Okay, phi. So this formula has this form. So it's a conjunctive Boolean formula. Okay, so it's in the form of this gamma 1, gamma 2, to gamma say m. Okay, by the way, this m is the input size of this formula. Okay, but I haven't defined this gamma j, right? I haven't defined this gamma j. So what is this gamma j? Okay, each gamma here. By the way, this is referred to as a clause. As a clause, okay? So this clause will have to be in the form of the following, okay? So every clause will have to be in the form of this, right? So let's say gamma j, okay? So this is gamma j. Let me put this gamma j here. Okay, so gamma j has the form of this. Okay, I haven't defined this L j comma 1 and j2, j3. I haven't defined them, right? But for now, you can think of each one of them as a Boolean expression. Okay, but what is really important here is that you can see that these expressions, they are connected by disjunction. Okay, so either of these expressions is true, and then this gamma j is true. Okay, but all the gamma j's will have to be true for this phi to be true. Okay, in that case, we say that phi is satisfied. Okay, phi is evaluates to 1, and then this means that phi is satisfied. So I still owe you this definition of this LJ1, LJ2, LJ3, right? So each one of them, each one of them is so each one of them is in the form of either xi or negation of xi for some I from 1 to n. All right. So this completes the definition of phi. Okay. Once again, you can see that this clause consists of 3 so-called literals. Okay. So these are called literals. So I'm going to. All right. So I'm going to use the following terms. Pay attention. So this phi will be referred to as a formula, the input formula. A formula is the conjunction of a lot of clauses. And every clause is the disjunction of 3 literals. And what is a literal? A literal is simply a variable or its negation. You see what I'm saying? All right. So this confines what expression you can give me, right? Good. Now, one more. Actually, this is not really a constraint. This is just to complete the definition, right? So this x1 to xn, so these are the variables, and every variable will have to be used at least once. Otherwise, you just remove it, right? There's no point talking about the variable. So if you look at the input size, right? The input size is m. Some of you will say 3m. That's fine, okay? But we will use m as the input size. So the goal of the 3-step problem is to find a way to set the variables to satisfy phi. Okay, all right. You can set x1 to xn, each one of them to either 0 or 1, and your goal is to find such an assignment, right? Value assignment, so that phi can be satisfied. Okay. By the way, the jargon, right? People don't say value assignment; they say truth assignment. All right, so I'm going to use the word truth assignment, the phrase truth assignment, right? So by truth assignment, I mean you set each xi to either 1 or 0. So that phi evaluates to 1, which means phi is satisfied. So this problem is, NP-Hardness. So let's look at a simple example. Let's say you have AB and then BC. Okay, so is this expression satisfiable? The answer is clearly yes. Okay, so let's say this is 1. You know what? To make things a bit more interesting, let's say this is negation of B. Okay, all right, negation of B. All right, so you can set this to 1 and B to 1 as well, and then this becomes 0 and C is 1. Right, so you can see this is satisfied. Good. All right. So once I point out the problem that can be reduced to John emptiness, the rest usually is much easier. Okay, so now this becomes an exercise for you to think about how to use a John emptiness algorithm to solve this. Okay? So I'm going to present the proof, but I don't think that's the main point here. The main point is, 3-step can be reduced to J, and then you can construct a proof yourself. So here is how we're going to construct a join. All right. So now we will have to construct Q. All right. So we're given phi. You see what I mean? You do not start with a join. All right. You start with a phi because you want to convert this phi to a join. And then you want to use a John emptiness algorithm to tell you something about this John. And then you utilize the result to return a verdict, to obtain, to derive a verdict on whether or not phi is satisfied. So here is the construction. Okay, here is the construction. So we want to create attributes, and we want to create edges. right? So think about the schema. And then for every edge, we have to define the relation. By relation, I mean the tuples, right? So here is what we do for each xi. So this is an attribute. Sorry, this is a variable. Okay. We introduce, so let's say design or introduce attribute xi. Fair enough, right? Okay, good. All right. So this is the set of vertices. Okay, good. Now, let's design the relations. Okay. So for each, now you consider every clause, right? So let's say the clause is gamma j. Okay, gamma j. You know this gamma j has 3 literals, right? And every literal uses one variable, right? Uses, so either xi or negation of xi, right? So I have the right to say, well, you know, let's just say that this clause uses, say, variables, let's say xj1, xj2, and xj3. Actually, this is confusing because this is a j, because according to my earlier definition, right, the subscript once fixed, and then the variable becomes fixed, right? But now this j comma 1 is not really an integer. You see what I'm saying? So I cannot really do things like this. So I will have to do something else. So I would say I1, I2, and I3. Okay. And this will make it clear. So I1 and I2 and I3, they are integers from 1 to n. Okay. And this is a fair statement to say because you have this gamma j and you must use 3 variables. They could be the same if you want, it doesn't really matter. But those variables, you know, each one of them has a subscript, right? So I get the right to say I1, I2, I3. So you can look at the sequence of definitions, right? So J first, and then I1, I2, I3 fixed. Very nice. And then I'm going to create a relation. Rj with schema xi1, xi2, xi3. Okay, so for example, in my running example here, AB, so you'll be creating a relation RAB, and here RBC. Fair enough? Okay, good. So here I have got all the edges already, okay? So basically you can see M edges, okay? Now finally, we will design the tuples inside the relations, okay? So let's say this Rj, what are we going to do? Well, now we have to look at the clause gamma j itself. Okay, so gamma j uses these 3 variables. Okay, and the content of this relation depends on how this clause uses these 3 variables. Okay, so in general, the content of this relation consists of all ways to make gamma j 1. All right. So what does this mean? Well, let's look at my running example, right? So let's say let's look at RBC. Start with RBC. So you know I will have a table with BC, right? But what values am I going to put into this BC? Okay, according to the definition here, I'm going to include all the values for B and C, basically choose the summing for B and C, so that you know the second clause evaluates to 1, right? So let's see, I got let's say I could have B in 1, so that will, I'm sorry, I can have B equal to 0, so that will make the first literal true, right? And then I don't care about the value of C, right? Right, okay. So on the other hand, if B is 1, and then C will have to be 1, so that the clause can be true, correct? Okay, so that is the table for RBC. Okay, so you can see you can have at most, I'm sorry, I said 3 set, right? So this is not really 3 set. Okay, so that's my fault. So let me give you another attribute then. Okay. So let's say D. Okay, so this is a 3 set now. Okay, so I have one more. Let's say A. Well, you get the idea. So there are a lot of tuples to construct. Okay, I'm not going to do it, but you get the idea. All right. So how many tuples can I have in this table? Well, at most 8, right? Even by a very, very rough count, right? If you want to be very precise, you can prove 7. But 7 and 8, they mean nothing to me at this point, okay? So, so the table will have a constant size, okay? Constant size, good. Which is important, right? Because I told you before, right? So I want to create this joint. I want to make sure that this joint, its size is polynomial in the size of this M, right? Which is the input size of this 3 set problem, right? So now you can see not only polynomial, this is actually linear to M. So okay, cool. So allow me to go back to 2 set because I want to make my point easier. Okay, in fact, the same construction holds on any set. Okay, so here. This is the table that I create for RBC, and then I will have to create the same thing for AB, right? Except that here, you will have these tuples here, right? So all the ways to set the values of A and B to make the first clause 1, right? Good. Now you have the joint. So now, next, you will have to prove an if and only if condition. Okay, if the joint returns something, and you definitely have a truth assignment to make phi to satisfy phi. Otherwise, you don't. Okay, I'm not going to present the whole argument because here it's already very straightforward. I'm sure this is not something you will find challenging. But just observe this to get the main idea here, right? So let's say you have this ABC. Oh, I'm sorry, this is actually wrong, right? You cannot set B to 1 in the first clause and then B to 0 in the second clause, right? You see what I mean? So what you have to do is so I was saying, okay, so I was confusing myself. Sorry about that. So basically, this is the truth assignment. Then indeed, yes, the value of this B is 0, and also it's 1 here. Okay, good. So now you can see we have truth assignment 1, 1, 1. Right? So clearly, since this 1, 1, 1, we have to make all clauses whole, right? So if you look at every projection, right, so this 1, 1, by how we construct the first table, right? So 1, 1 will have to appear in this table AB, right? And same, right? So BC will have to be there for BC, right? So therefore, you can see one direction holds, right? Okay, and the other direction follows the same. So yeah, that's everything I have for today. So this is the beginning. Okay, so just a very quick advertisement for next week. So next week we will, the next 2 weeks, right? We will focus on cycle joints. Okay, so if you think about the construction here, okay, if you think about the construction here, it crucially relies on the fact that the joint can be cyclic. You see what I'm saying? Okay. So as I will show you, if the joint is acyclic, then there is a polynomial time to compute the joint result. Actually, there is a polynomial time to detect emptiness. So this also means that if you give me a 3-set input, and the 3-set input has a corresponding acyclic joint, and then the 3-set problem is actually solvable in polynomial time. Okay, all right, so this proof, as I said, right, says nothing about the computational hardness of acyclic joints. So the next week, the next 2 weeks, we'll focus on acyclic joint. But if you think about it, there are two issues we must resolve in order to say that we have solved this acyclic joint problem. The first one is I give you a joint. How do you know it is acyclic or not? You see what I mean? You are able to generate a schema graph in polynomial time, that's for sure. But then how do you know this is acyclic or cyclic? You see what I mean? So that's the first thing we will do. Okay, so next week we will tackle this. Okay, so the idea is to eat a little bit every week, right? So not to get fed up, right? And then if you see, okay, this is indeed acyclic, the next question is what algorithm would you use in order to compute its result? Okay, so that will be 2 weeks later. All right, thank you guys. So this is everything I have for today. See ya.